Okay, so as promised, today we will go over an alternative solution for test 3 on your question. Does someone have a test with them? Thanks. So if you recall, our dynamics were m times 2 plus cosine x times x double dot minus 1/2 mx dot times x sine of x plus L cosine of x equals our control input tau. And we said that our to quantify our objective, we define an error signal as E equals xd minus x. And then to further facilitate the Lyapunov analysis, we defined a filtered tracking error. And by the way, right here is why it becomes non-autonomous, because now you've done a variable transformation from x to e, that's e of xt because of xd. So some of you may be wondering that. So then we design a filter tracking error, which is r equals e dot plus alpha e. And by the way, some people look at this and have a concern because it looks like there's mixed units. Right, I've got velocity plus a position here. And that's a little concern because alpha can be a unit conversion factor and a control gain. So alpha can kind of wash away all those concerns. Okay? And we said in the last class we went over a solution where we said, okay, since this is kind of a disturbing term, makes us have to scratch our heads a little bit and spend some time thinking about it, why not just get rid of it? Because it's always positive and it's a known measurable thing. And so that was the solution method that we took in the last class, which was probably the easiest solution method we could have taken. But it's not the only way we could have done it, because some people looked at this and I think they probably immediately said, okay, this is like m of x. And we looked at some problems like that in class. And so let me develop it that way. Okay, so which is not a bad way to approach it. So then these people said, well, if I look forward to my Lyapunov analysis, and I know this is going to be hard for videotaping. If I look ahead to my stability analysis, I know that when we went over these things in class, we had like a 1/2 mr squared kind of term. And then when m became time varying, we had to put the whole time varying thing in the Lyapunov function. All right, so now I'm going to have to develop a closed loop error system that's going to be like an m of x times r dot kind of thing. So if I said m times 2 plus cosine x times r dot, this would equal to m times 2 plus cosine x times xd double dot minus m 2 plus cosine x times x double dot but then I'm going to replace this term here with minus 1/2 for my dynamics, minus 1/2 x dot times x sine of x plus L cosine x minus tau. And then I'm also going to have plus m2 plus cosine x times alpha e dot. Okay, now just like I did in the last class, I can look and say, okay, there's an unknown term, there's an unknown term, there's an unknown term, there's an unknown term, but I know everything else, so I could go ahead and group all of this into y theta and then continue the design just like I did in the last class. However, there's a caveat in this approach. And that's because when I do the stability analysis, now I've got this time varying function up in here. By the way, it's okay for me to put m of x because this is always positive, right? 2 plus cosine x is always positive. Because when I take v dot, I'm going to get 1/2 m dot r squared plus r times m of x times r dot. And we know we're going to have an adaptive estimate mismatch, so we might as well go ahead and put that in there. And we know this is going to equal to negative theta tilde transpose times theta hat dot. So this piece looks just like the piece did when we did it in the last class, when m was a constant. But because m's not a constant now, we've got this m dot term here to take care of. Okay? So, well, the way we usually take care of this m dot term is we use the property that says 1/2 times m dot epsilon transpose 1/2 m dot minus Vm times epsilon equals 0. Normally we use this property to take care of that m dot term there. So if we examine our open loop air system, we have to look and see, well, can we use this property? Well, first of all, what is m dot? In this case, m dot is going to be m times negative sine of x times x dot okay? And we've got 1/2 multiplied by that. And so now, is there anything like this in my open loop air system? That clever test designer snuck this term right here into my dynamic model, which is my Vm term there. Right? So this term is kind of like the Vm term. You see that? This is equal to that. Oh wait, where did this extra x come from? Oh yeah, that's right. Oh, wait a minute. Not quite, right? It's not quite the same, but it looks real similar. So I've got this term, and epsilon here is going to be an r, right? So I'm going to have r transpose times this, and we want to have another r over here, but we don't yet. And we're saying we're going to subtract from this Vm term, which I'm calling negative 1/2 m x dot times x sine x. But I hope I don't work myself into a trap doing this on the fly here, this hard way.
How did you get from the property down to before you put the R transpose? What was the 1/2 m? Where did that come from?
So this piece, oh, actually I do have my r squared, don't I? So this piece here is equal to that piece there. Make it simpler on ourselves. R is a scalar in this case. Okay, and so now I'm trying to find something in my open loop air system that will cancel with this term. I love doing math on about 4 hours of sleep. So this 1/2 term and this 1/2 term are okay. I've got a negative sign up here and a positive sign down here, so those can cancel. The m looks like it's going to cancel. The sine x term looks like it's going to cancel. The x dot term looks like it's going to cancel. But now here I've got r squared. Over here, when I put this in the Lyapunov, when I substitute this into my dynamics here, I'm going to get an r times that. So I'm going to have an r times all this stuff. But up here I've got an extra r, and down here I've got an extra x. Right? So I need to do some manipulations. So I know that r equals E dot plus alpha xd minus x. Or I can say that x equals E dot plus alpha xd minus r, where this over alpha, this alpha cancels, and that's over alpha. Is everybody following along there? Checking to make sure I don't make a mistake. So this is my expression for r by definition, and I'm just solving this for x. Right? Does everybody agree with that? Okay. So now I can plug this stuff in here. And I can rewrite this expression now as minus r times, well, this minus and the minus are going to cancel. So it's plus 1 plus r times 1/2 m x dot times sine of x times x, which is E dot over alpha plus xd minus r over alpha. I'm making a mistake in my signs here. There's so many ways to do this. Minus. Yeah, I just don't like that. You know, I'm going to make life simple on myself. Let's take a step back. So I still want to use this property. So I'm going to need a, I already have 1/2 times m minus sine of x times x dot. That's this piece right here. And I already have my epsilon transpose epsilon. That's my r squared. And so now I'm looking for this term. I'm looking for a term to cancel that. So I'm looking for a plus 1/2 m sine x dot times r squared. Okay? So if I want to have that, then I'm going to come down here and I'm just going to add and subtract it. It's just the easiest way. So some terms will cancel between these two, but without getting in a big algebraic quagmire here, I'm going to do it this way. So I'm going to add this term, and I'm going to subtract this term. Okay? Fair game? So instead of going in here and trying to work out all the algebra, which would be the nice thing to do, the efficient, the better control way to do it, I'm just going to, for the sake of simplicity, I'm just going to add and subtract a term. And I've added this term right. I've added this term right here that I wanted to have in there. And so you can see that this circled term and this box term up here have a lot of common terms in them. So all of this can be factored out, and you'll get r plus x left over. All right, so let's go back over. Let's continue with the open loop error system over here. So I've got m times 2 plus cosine x times r dot equals m times 2 plus cosine x xd double dot minus 1/2 m x dot x sine of x plus L cosine x plus m on the 2 plus cosine x times alpha e dot minus 1/2 m sine x x dot times r plus 1/2 m sine x x dot r. Is that everything? Did I leave off any terms? 1, 2, 3 minus torque. No. So this x double dot term, I substitute the dynamics in to get these terms. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. So now, I like this term here because I injected it. I added, subtracted it. And I injected it here because it's going to cancel with my m dot term in my Lyapunov analysis. All right, so I'm going to leave this one alone. And then I'm going to take all the terms in the box, which are all measurable. R is measurable because E dot is measurable and E is measurable. So I'm going to take all the terms in the box, and all the terms in the box can be linear parameterized as y theta, right? Because this M, this M, this L, this M, and this M would all go into theta, and the rest of the terms would be collected into y. Okay? So y would be a 1 by 2, and theta would be a 2 by 1 vector. Okay, so let me come over here and design my control input, which is now pretty easy because I've got m times 2 plus cosine x r dot equals y theta minus the torque minus 1/2 m sine of x dot times r. Okay, so I'm going to design my torque is equal to y theta hat minus kr plus kr, and that's it. Same torque as I designed for the other method, but maybe y theta contains a little bit different terms, or y contains a little bit different terms. So now my closed loop air system can be written as m times 2 plus cosine x r dot equals y theta tilde minus kr minus 1/2 m sine x dot r. Okay? So now come over to my stability analysis. Now I've got v dot is 1/2, and we said m dot was equal to m times minus the sine of x times x dot times r squared plus r times, now substitute in my closed loop dynamics from over here, which is y theta tilde minus kr minus 1/2 m sine of x dot r minus theta tilde theta hat dot. Okay? So, looks like I should have made this positive. Looks like I should have used the negative one in y theta and kept the positive one out here. So now this term cancels with this term by design. This is my negative feedback term. And now I need to cancel this ry theta tilde term. So now I can design my theta hat dot is equal to y transpose times r. So when I substitute this in here, I'll get negative theta tilde transpose y transpose times r, which is a scalar. I take the transpose of a scalar and I get r times y theta tilde. So this term will cancel out that term. Wow, that was a painful exercise. But is there any questions in general?
The filtered tracking error, would you say that that's a technique for performing these analysis, or is it actually required in order to?
It's not required. You could have written this in state space form and done it in an awkward state space form. You could have included, instead of having in your Lyapunov analysis 1/2 mr squared, you could have had 1/2 1/2 e squared plus 1/2 e dot squared. You could have done it that way. The use of the filter tracking error is mainly reduces your bookkeeping and headache. It just kind of condenses it and allows you to have your control objective is a first order control objective. You have second order dynamics, so it just allows you to include your first include your E and E dot in here, so just one derivative will give you your second order dynamics in here. And I could have, by the way, I could have had another tracking error, filter tracking error that said R2 was equal to R plus alpha E dot. Is that how that would work out? That's E1, that's E2 plus alpha. Yeah. So I could have had another filter tracking error if I wanted to, if this was even a higher order objective here. So then when I would have taken the derivative of this, I would have gotten, oh, dang it. That's this E1, I called that E2, and this would be E2 dot plus alpha E2. Okay, so this would be, so I can have an R2, this R plus alpha R dot. R dot plus alpha R. So doing it this way, when I take my one derivative of my R, then I get my E double dot, so that's for second order systems. But I could have done another filter tracking error here where I've got R dot, so if I were to take the derivative of R2, then I have R double dot, which would have been E triple dot, so that would have been for a third order system. And so I could have successive, I could have R to the n equals R to the n minus 1 dot plus alpha R to the n minus 1. So I can have successive filter tracking errors if I want to, because I can look at this one and I can show that if R2 goes to 0, then R dot and R will go to 0. If R goes to 0, then E1 dot and E go to 0. So it just cascades on itself. Are there any questions about the filter tracking error? Any questions about the design process in general?
I still am not sure how you got that, how you used that 1/2 and
Okay. So yeah, I did kind of bunk that a little bit. So let's review it really quick. So I'm worried because I didn't use the first approach, and I'm using this alternate approach.